kira masa. Tu orang main-main. Hello, Assalamualaikum. Dah dengar?
Sana dah dengar dah.
Okay, very good morning to all of you. So we are going to start our class. I would like to apologize for the delay. Could you please switch on your camera? Turn on your camera, please. So Mr. Azwan, so how is the attendance today?
Ya, Doktor.
Mr. Raja, seorang je ke hari ni?
Seorang
Seorang
doktor.
je. Mana lagi seorang? Syafiq dah asing. Tak share satu komputer ke hari ni? Azwan?
Hari ni
Doktor.
wifi elok sikit.
Oh, ya ke? Ya Allah, Alhamdulillah. Azwan?
Total 25.
Total 25. Dah, 26 ke? Cuba kira. Twenty, 2, 4, 6, 7. Ada yang buka 2 kot. 27 je?
Fazlika buka 2 kamera.
Fazrika, dia memang tamak tu. Dia tamak teknologi. Fazrika tamak teknologi. So, very good morning to all of you. I'm happy to see you again today. So without further ado, we will start our class with the dua.
Where's the door? It's gone. Wait. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيده يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على سيدنا محمد وعلى آله وصحبه أجمعين اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا اللهم اجعلني في قلبي نورا وفي لساني نورا
وفي بصري
وفي سمعي نورا وعن يميني نورا وعن يساري من فوقي نورا ومن تحتي نورا ومن أمامي نورا ومن خلفي نورا واجعل في نفسي نورا رب اشرح لي ويسر لي أمري رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin, Amin, Ya Rabbal Alameen. Thank you so much to Mr. Akasha. Without further ado, we will start with our class today. So I will continue with the topic 7. Let me first share my slide, and you can also refer to your own PDF, yeah? Right. I hope you can now see my slides, right?
Yes, Doctor.
Okay. All right, very good. So we are in non-isothermal reactor conditions, and the two terms that we are going to be using for the whole chapter is adiabatic and non-adiabatic. You have heard about these two terms since the last lecture, lesson 1, week 11, but I hope you have also tried to ask yourself, how does adiabatic and non-adiabatic looks like? Yeah, but before that, we are going to go to the issues that saya lupa lah about ni. Lupa sungguh. But anyway, I'm going to repeat the issues, and the issues are actually the hint for you to visualize. Oh, lupa lagi, sorry. The hint for you to visualize how the reactor system would look like, yeah, for adiabatic and non-adiabatic. So please stay focused, yeah. I'm so sorry for this few slide yang hantu ni, I terlupa lah nak figure out. So I'm going to repeat the issues, yeah. So for adiabatic, the issues would be when T varies along the PFR, meaning if you have your PFR, the T varies, yeah, as you go along. It enters, then it goes out, then the temperature changes. Temperature 1, temperature 2, temperature 3, and so forth are not the same. Yeah, that's the hint. And when heat is removed from a CSER, but of course, you know that for an optimized production of certain product, let's say a highest conversion, you say you want it to be isothermal. You don't want the temperature to change, let's say. So you imagine having this condition, but controlling the temperature. Yeah, but in this case, for adiabatic, we are going to design as such that if it's to be isothermal, what do we do? Yeah, if it's not that specific, saya tak nak bagi jawapan lagi. Saya nak initiate your thinking first. Yeah, if the temperature changes, why do you make it that way? You tak buat apa-apa. Biar je sepanjang, let's say PFR, temperature to changes. There are reasons for that. Yeah. So if you go to our next slide, another issue that we can relate for a diabetic, meaning you allow saja the reaction to temperature changes. Katakan exothermic, if it's exothermic, as time increases, the temperature will increase, yeah, because it release out heat, yeah. So we are going to relate, if you have that kind of case, the relationship between the temperature is very crucial to be connected to conversion and also the reaction rate, yeah. I think for this class, I did not mention about the interstage cooling in detail yet, but I'm going to touch it a little bit today, meaning, let's say if you have your PFR, it's adiabatic, temperature changes, then it enters with a certain X, then it will give you at certain final X. Yeah, let's say if the final conversion here is not your targeted conversion. So what do you do for this kind of reaction? In this case, temperature masuk and temperature keluar. Temperature final is greater than your temperature initial. But then your conversion XF is also lesser than XI, but your XF is not your targeted XF. You're not your targeted conversion. What we can propose is that why not if we introduce, let's say kat sini masuk to another PFR, let's say, but then it will enters with, it will enter the second PFR with TF from the first PFR. However, since isotonic, TF here is so high, yeah, nanti dia jadi lagi high. But we know that from this PFR, as T increases, X increases. So the trick is, why not if we introduce heat exchange equipment here, which will cool down the hot temperature from the first PFR before it enters the second PFR. And we know dia masuk, dia dah turun sini sebab ada heat exchanger, dah sejuk kan. Then because of the exothermic nature, the temperature of course will increase. Then the TF2 here will also be greater than inlet. But the inlet here for the second PFR, we have cooled it down with the introduction of the heat exchanger. But the XF here, of course, you cannot cool it down, you cannot do anything. It's something that you have achieved. Then XF2 is somewhat increasing than the XF earlier here. All right, so that's a trick. So this is what we say as interstage cooling for an adiabatic system. All right, so if let's say this XF is not yet achieving your target conversion, you may repeat the same process, introduce heat exchange equipment to cool it down, and before it enters the third PFR, then let it be exothermic because it's adiabatic, and the final conversion will of course be greater and greater. Yeah, so you may have an interstage cooling in between of series of reactor to achieve your targeted conversion. Yeah, this is specially done for an adiabatic system. And to take note that this part will be covered at the last part of topic 7, which is also very crucial. Yeah, this is what I'm trying to say here. Then of course, we because of that condition, we want to determine the optimum inlet temperature to achieve Xmax. So this is what we say about Xmax here. So in this case, the X achieved from the first reactor is not yet your maximum conversion. Yeah. So you may introduce series of reactor until you achieve your maximum conversion. Since it is adiabatic, then the interstage cooling may be introduced and recommended. All right. Okay, if you have any questions, this is such a very interesting part because this is the practical of design of the reactor itself. If you want to increase the temperature dealing with an exothermic condition, especially for this kind of adiabatic condition, yeah. So we're going to go to the next one, non-adiabatic system. So the issue would be for PFR with heat exchanger operation. All right. So non-adiabatic means it says there that these are the hints, yeah, how the non-adiabatic look like. In a non-adiabatic system, we may run or operate our condition at a constant fluid temperature, even though it is not isothermal, but we introduce a design to that reactor that will allow the temperature to be constant. All right. For that fluid temperature of the reactor or the reaction. But we have a variable fluid temperature at a co-current or counter-current operation. I think you have taken your heat transfer class, haven't you? Bila? This semester ke? Heat transfer.
Last semester.
Lah, ah? Oh, diploma. Lupa kamu. Diploma. Okay. Akasha, bila Akasha?
Last semester, Dr. Sem 3.
Last semester. So you may have encountered these terms, right? Co-current, counter-current. Seronok pula tanya. Tanya Kasha lah sebab dia baru belajar last semester. Yang lain diploma like years ago, you know. Betul tak? Betul tak? No nada. Nak I tanya you, no nada? Tak nak. Tak aci. Yeah, Kasha. Akasha. So what is co-current and counter-current? Kalau Akasha tak boleh jawab, Raja siap. You kena jawab soalan I. Rasa jadi lecturer kan? Lesson 1. Co-current, counter-current. Raja. Mana Mr. Raja? Akasha, cepat jawab Akasha.
Co-current is when you have two inlet stream going in the opposite direction, like current. They call counter-current. And if co-current, meaning they go in the same direction, like the reverse, like that.
The counter and the co-current means the direction of the movement of the fluid. Okay, the fluid refers to what fluid?
It refers to the cooling and what is the one? I remember the cooling medium and the one that needs to be cooled or heated.
Okay, take note, yeah. In chemical plant, the cheapest cooling fluid means gas or liquid, yeah. So the cheapest cooling fluid is always water. But then if your delta T is too high, so you need to cool down to a very high, from very high to very low temperature, then of course you need coolant, yeah. Coolant is a special fluid. Tapi kalau delta T tu tak berapa besar sangat, of course you from the delta T acceptable, then you will just need to use water. So this is what we are trying to say. Mr. Raja, are you ready, Mr. Raja? Mana Mr. Raja? Tadi dah ada muka, sekarang tak ada muka pula. Raja. Oh, Raja. Nada tengah sebelah, macam dekat je duduk sebelah mana Raja tak ada. Raja tak boleh jawab, Syafiq jawab. Syafiq house doormate. So we are actually right, Mr. Akasha. We are talking about the direction of the coolant. And that coolant is used in a heat exchanger equipment. And there are many kinds of heat exchanger. It can be evaporator, it can be heat exchanger. Heat exchanger is a heat exchanger, shell and tube. Can be many other kinds of heat exchange equipment. So we are talking about here, the last statement is talking about the temperature, the fluid temperature of the coolant. The coolant can be the cooling fluid lah, coolant ataupun water, yeah. So you can imagine that in a reactor, naturally it is having increasing temperature. The temperature changes, but because of that, we make a special design for that reactor such that during the reaction, the temperature is constant. It's maintained. As temperature rises, coolant ni lah to absorb the temperature, yeah, with a proper control. You in control. You in what that design, yeah. So because of that, the fluid temperature in the heat exchange unit will vary because it keeps absorbing the fluid, the heat being released by the reaction. Take note, the hint there, heat being released by the reaction. So we will have a look in the upcoming slides what terms that we are going to take into consideration when we are dealing with non-isothermal condition. Okay, I'm going to go to the next slide. There are a few more issues. So because of that, we consider steady state temperature and X for CSCR because we design that reactor to be non-adiabatic and dealing with multiple reactions with heat effects. Due to when we have multiple reactions, then of course we can consider the heat effects, yeah, the non-adiabatic condition to the reactor. And again, in this topic 7, especially chapter 11, the last part would be discussing on the gradients or the change of radial and axial temperature and concentration, such an unsteady state condition here, yeah, that we are trying to understand. Now, as I said earlier, frequently we will see this non-isothermal condition or adiabatic being carried out in industry. The question is, how does adiabatic system look like? Yeah, with the keyword here, with heating or cooling either upstream or downstream. Okay, that's one keyword. The second one, non-adiabatic. Heat added and removed from the system varies along the length of the reactor. Meaning, if for a non-adiabatic system, ni you engineer ni, you yang kata you add heat or you remove heat in your reactor during your reaction. Itu maksudnya. You remove heat because it's exothermic. The temperature increases during the reaction. You add heat, maybe it's endothermic. Yeah, the heat is being absorbed. Yeah, makin jadi rendah temperature. Yeah, from the system which is varying along the length of the reactor. So that would be the hint, right? If I go back, adiabatic with heating or cooling either upstream or downstream. Okay, agak-agak you boleh teka tak before we really go into the real business. We want to have an idea how does adiabatic look like, how does non-adiabatic system look like, especially reactors. Siapa nak teka? Tadi kita duk tanya Mr. Raja ni tadi tak kelar-kelar. Nantilah kita tanya dia. Dia buka kamera je kita tanya. Okay, Azra. Nak teka? Agak-agak macam mana rupa adiabatic system dengan non-adiabatic reactor or adiabatic reactor? Azra?
Saya doktor.
Yes.
Adiabatic tu dia macam dia tak ada any changes ke? Kan?
Tak ada any changes of what?
Macam dia punya mass in, mass out. Lepas tu
Is in, mass out?
ya ke? Ke saya silap? Saya dah lupa doktor.
Okay, the hint. Hint lagi sekali ya. Okay, non-adiabatic lah. Heat added and removed from the system. Non-adiabatic. The opposite maksudnya kita tak add or remove the heat during adiabatic in an adiabatic reactor lah. Itu je maksudnya. Okay, sahabat teka. Afsar. Doktor, saya ada tanya soalan ke doktor? Doktor, ada tanya saya soalan ke doktor? Raja tanya. Sorry doktor, saya start dari internet. Ya, ada problem sikit. Alah, kesiannya. Okay. Siapa nak jawab, Afsar?
Reaktor tu well insulated.
You are close to it. Okay, for which one?
Apa doktor?
Which one? Adiabatic or non-adiabatic?
Oh, adiabatic. Adiabatic. The reactor or the system is well insulated to prevent of heat exchange from the surrounding to the system.
To prevent the heat exchange from to the system. Okay, that is something else, yeah. Well, insulation is somewhat that you use to prevent the heat from, let's say, outside coming in. But now we are talking about energy being used to take that heat out. Let's say exothermic. How do you relate to that? Insulation is something else. Well, it's close, but we're not yet to the question that I asked. Okay, I'm gonna go and ask you to have a look supaya you dapat hint Okay, mari kita tengok textbook. Dalam textbook dia tak cerita, okay? Tapi you have to understand it yourself. Kejap. Katakan 4th edition. 4th edition chapter berapa Chapter 6 You pegang edition nombor apa? Ni topik apa ni? Okay, non-isothermal. Okay, chapter 8 lah. Chapter 8, I'm going to go and ask you to have a look at this one, at one drawing. Saya nak tanya kamu, ini diabetic ke non-diabetic? Sekejap ya. Hold on. Okay. Fourth edition, table 8.1. Apa ada fourth edition, table 8.1? Saya tengah nak buka fifth edition jap. Anyone who wants to answer? What do you see? What do you see? Apa yang kamu nampak? Table 8.1 untuk PFR with heat exchange. Oh, CSTR with heat exchanger. Anyone? The 11. Fifth edition is chapter 11, 493. 493 ya. Senyap je, tak cakap apa. Kamu tengah baca buku dengan tekun ke? Fifth edition muka surat berapa Fifth edition muka surat mana ni chapter 11 Oh, tak sama muka surat ke? Okay, I'm coming. Coming. Oh, tak sama. Sekejap. Okay. Screenshot sekejap. Okay. Saya enlarge kejap. So what is this? Okay, what is this? So can you see the drawing that I'm sharing here? It's a PFR or PBR. PBR means spread backed. This is bed, packed. So here we have the packing with the catalyst. So the whole thing is a bed of packing. So this one is PFR, yeah, plug flow reactor. And you see that the reactor itself is the inner tube, yeah. The inner tube is the reactor. The outer is the flow of the exchanger, yeah. Maybe a coolant. So coolant you masuk, keluar. Coolant. So coolant you masuk, keluar. So actually the coolant is surrounding your reactor. Okay. So this is the reactor where during the reaction, the heat is being removed or added. So if we are talking about coolant, so the heat is being removed. So directly you're saying maybe the temperature increases. So you don't want that high temperature. You want it to be a constant temperature. So that is why you surround it with, you design as such that the hollow tube is where you fit in your feedstock. Yeah, your feedstock having your A, B, C, D, blah, 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 blah. This is maybe water, simply water, yeah, simply water. If you need to cool it down even way lower that from a high temperature, then maybe you use a special coolant, yeah. Water is a kind of coolant as well, yeah, very cheap, the cheapest coolant of all, you can simply use water if that could work for your reactor. Yeah. So this is an example of non-adiabatic system. But now my question would be, how do we imagine an adiabatic system? Macam mana pula? But then we have heating or cooling either upstream and downstream. Macam mana pula? Let's say you have A plus B from another plant. And that A and B from another plant is a kind of unwanted side product. So you bring it to another chemical plant that you want to use this for a certain product, which you say boleh jual ni. Okay. And this one may have certain temperature. And you introduce it to CSCR or PFR, right? So you say at that PFR or CSCR, it needs to be fit in at a certain temperature initial. Tapi ini mungkin you dah store dah, you dah simpan dulu sebab it's a waste from another chemical component. You simpan dulu. So sekarang you nak bawa dekat chemical plant lain, so it's now at room temperature, let's say. But naturally, to produce C and D, the best temperature to start with is not room temperature. So you're bringing it to another chemical plant, maybe you use CSCR or PFR. Then it has to be at katakan 100 temperature. Alright, inlet. So what do? Ni buat apa? Tadi you dah store dah dalam storage. It's a waste from another chemical plant. Sekarang you tak nak buang, you nak produce a new product. So you nak masuk dalam reactor balik. And you know that the inlet temperature must start with a higher temperature. Let's say from your science reading, scientist kata it should start at 100. But daripada chemical storage you dah store dekat 25 degree C. So what do? Ni kerja engineer lah semua ni. So what do? Fazlin. Okay, Afsar. Yes, Afsar.
Kita buat proses heat transfer, mungkin jadikan dia sama ada coolant to absorb heat daripada daripada produk lain, daripada kilang tu, untuk buat heat transfer supaya dia punya temperature naik.
Alright, very good. Ini Afsar punya jawapan ni, sebenarnya jawapan dia dah memang advance daripada kelas ini. Advance daripada kelas heat transfer pun. That is the answer for class process integration. Okay. Maksudnya, the simplest way is to introduce heat exchanger. Alright, sebelum dia masuk daripada 25, jadikan dia 100. Then baru dia masuk dia punya CSTR ataupun PFR at 100 temperature inlet. So this is an example of an adiabatic system. But then Afsar, dia dah pergi over daripada scope tu, dia dah jawab benda ni, dia kata, the question would be, okay, I'm going to use heat exchanger. And that heat exchanger, masuknya 25 degree. Sekarang you nak dia keluar daripada heat exchanger to become 100. So how do I do that? I need to introduce heat. And that heat simply, kata you guna water, you kena heat the water up and to 100 temperature ke apa ke, or more, even more. Water tak boleh lah sebab you nak 100 kan. So you need another specific gas, hot gas. And inilah yang Afsar jawab. Mana you nak dapat hot gas ni? Most probably that hot gas is actually obtained from, or maybe gas biasa, tetapi the heat comes from additional heat from other process line yang jadi waste. So you tak nak buang energy you salurkan masuk dalam heat exchanger you. Remember in your heat exchanger there are shell and tube. Remember, if you don't remember, kalau yang dah diploma tu mungkin dah lama, Akasha mungkin dah ingat, masih ingat lagi. Your heat exchanger ada shell and tube. So you should know your fluid gas suitable in shell ke in tube ke. Your fluid liquid suitable in shell ke in tube ke. your fluid yang you nak panaskan tu sesuai masuk dalam tube ke, masuk dalam gas ke. So let's say in the shell, liquid, so the gas or gas from shell, tube, liquid. So maybe your shell is your hot gas. To get your hot gas, you use additional heat from other process line. So this is what APSA is trying to tell you. So this is what you're going to learn in semester 6 code in process integration. And you are now in semester 4. Very good. Yeah. So try to imagine this even from the beginning. Do not simply learn, oh ada batik tapi tak boleh bayang sistem dia macam mana. Can you get an idea now? Syafiq Abu? Syafiq
Yes.
Abu, dah faham ke?
Faham?
Cuba cerita apa benda?
Oh. So basically kalau kita nak daripada mana? Kalau yang biasa ni kita guna heat exchanger. Tapi kalau kita nak buat saving cost, so kita akan pakai heat daripada reaction lain dan kita contactkan between the two pipeline ataupun basically two pipeline lah. Saya dah lupa term dia, tapi basically kita increasekan temperature tu.
Yeah, very good. So basically you increase the temperature before it enters the reactor. So the heat exchanger equipment is introduced before it enters your reaction or your reactor. So the whole system is adiabatic system. But for non-adiabatic system, the heat exchange unit is together with your reactor. Okay? Okay, another example would be if you look at table 8.1, the same one. Before that, you see a figure CSCR with heat exchanger. So that is non-adiabatic system. Boleh nampak ah? Iaitu in your heat exchanger, so kita
Doktor,
ada coil, cooling coil or heating coil inside your reactor. Yes, Mr. Afsar.
maksudnya kalau non-adiabatic ni kita punya heat exchanger tu ataupun heating element tu akan sekali dalam reaktor. Lepas tu adiabatic proses ni kita punya heat exchanger ataupun heating element tu akan berlaku sebelum proses tu, sebelum kita punya bahan tu feed masuk dalam reaktor. Betul ke doktor?
Correct. Very good, Mr. Afsar. Okay, clear to everyone? Yeah? Okay? So, that would be the introduction about adiabatic and non-adiabatic. So, I'm so sorry sebab the last class petang tu I was so weak actually. Try my best to teach you tapi saya pun macam lalok-lalok. So, saya bagi you leisure activity, yeah. I don't know what happened to me the last few days that week, but of course I still come to class, senyum-senyum, tapi badan cannot cope, yeah. So, if I remember teaching you with a very less teaching information, macam baca-baca je gitu. So, I feel so sorry for that, yeah. Alright, so we're going to go to the energy balance. So, this is what we are trying to say in topic 7. For non-isothermal system, we are dealing with removing energy or adding energy. Yeah, remember when you learn in your heat transfer class, you use this alphabet Q, right? So you're talking about the heat transfer, and that capital Q is your heat transfer. Yeah, and then of course your heat transfer tu ada conduction, ada apa lagi? Ada radiation, ada convection, blah 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 blah. Well, I'm not going to go into details. Yeah, of course, conduction ada formula dia. Radiation also with that formula. Convection also with that formula. If I ask you, you still remember the unit for the heat transfer rate. Heat transfer rate. So what is the unit? You still remember? No, nada.
Tak ingat.
Tak ingat? Azri. Akasha, you kalau tak ingat saja, baik you cari jawapan sebelum sampai turn you. Azri. You belajar last time, Akasha. Azri.
Tak ingat doktor.
Azian. Tak ingat juga. Amani.
Joule per second ya doktor?
Joule per second
Ha.
ke?
Yes. Azri and Amani answered joule per second. What is the other name for joule per second?
Watt.
Yes,
Ah.
Akasha, finally. Watt. So it's actually joule per second, the watt. So this is what you are going to also do in your topic 7. All right. So this Q is actually the heat flow to the system, either coming in or coming out. The E circumflex is the change of total energy of the system. When we talk about energy, not only the energy from the heat exchange, the energy could be from the work from that heat. The energy could be from perbuatan, physical, being work lah. Maybe if we have CSTR, maybe the work from the impeller, yeah, that could be also an energy. Then to work the impeller, you need electricity. So the energy could also from electricity. Okay, the energy could also be by the movement of the fluid, yeah, the flow in. That could be some kind of energy as well, the movement itself. So we have a very general energy balance for a closed system. The change of the E circumflex, which is the change of the total energy, what's going on inside, is simply the heat flow to the system. So this symbol it's just to say that the change, ya, dia bukan simbol untuk differential terms, ya, bukan simbol untuk yang mathematical differential tu, but it's just to say change, ya. And then del W is the change of the work done by the system on the surrounding. So if you go into details, a closed system simply that, yeah, with the Q and with the work. But when you allow the system to receive, to accept flowing in, and of course it will go out, then you call it an open system. So for a continuous flow reactors, we can write the energy balance based on an open system, meaning you have flow in, you have flow out. Then because of that flow in and flow out, we are going to introduce a new term here, which we call it as enthalpy. Yeah, enthalpy due to that energy. We'll go into that in detail. So if you go to the next slide, it shows you on the basic energy balance equation. Remember for your topic 1 until topic 6, you write all the way the mole balance, yeah, from your basic flow in, flow out, then the change of the reaction rate, yeah, and so on. Same goes to the energy balance. We write the change of the energy through time, yeah, within the system. So we call it rate of accumulation of energy. Simply the Q, rate of flow of heat coming in, or from the surrounding, then or minus the work done to the system on the surrounding, and plus the rate of energy added to the system by the mass flow. The keyword here is mass flow into the system. That's why you have plus. That if it comes out, then minus what is coming out, which is leaving the system. What is leaving? The mass flow. So how do we write the mass flow? It's simply how much mole per second, because you have your fluid coming in. So we need to know how much mole per second. Since we want every term to be joule per second, so this term must be multiplied by joule per mole. How much of that energy joule per mole. So you get joule per second, yeah? And that joule per mole is called as E, yeah? E, which is the energy that we use here, joule per mole. Okay, the next slide. Sekejap, yang ni dah habis hantu ke? Sekejap ya. Dah habis dah. Lega, baru besar sikit. Okay, the next one is, that is the equation that we predict, yeah, for an open system. The heat coming in, the work coming out, the flow, the mass flow coming in, the mass flow coming out. All right. So you have that system, the mass flow, the rate of energy. Here we have the energy, and that energy is either your internal energy, kinetic energy, or potential energy. All right. Yang masuk dan yang keluar. The work could be, I'm going to go to the next slide to elaborate on the work. The Q is simply your heat. Your heat too, whether you add your heat or you remove your heat. Okay, if it's an adiabatic system, Afsar, where is Afsar? 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 Mana Afsar?
Ya, doktor.
Mana muka you? Okay, saya ada soalan untuk you. If it's an adiabatic system, you know in your reactor, your heat exchanger is separate from your reactor, right?
Yes.
Do you have heat added or heat removed in your adiabatic system?
Adiabatic heat
Hmm.
added.
Azri dah jawab dah, tapi I tanya Afsar, nanti I come to Azri. Azri dia tunjuk sign language. Afsar, heat
Yes.
dalam adiabatic, heat added ke, heat remove ke atau tak ada?
Oh, untuk kalau supposedly untuk adiabatic no heat or energy
Okay.
transfer.
Very good. So Azri, what would happen to the Q?
Q is 0.
Yes, very good. Siapa tak boleh bayang lagi? Afsar dah OO tu betul ke Afsar faham? Afsar pula Kasha. Faham?
Faham kan?
Ni tengok tu masih kod-kod pula. Azri cuba cerita Azri.
Doktor, kita pasal adiabatic.
So for an adiabatic system, what happens to this Q?
There's no heat is flow in or flow out in the adiabatic system. So Q is 0.
Yes. If it's an adiabatic system, there is no heat being added or heat being removed. Kita biar je dia react. Okay, doesn't matter lah temperature dia nak naik ke, temperature nak turun ke, naturally buatlah kerja dia. Alright? So you are actually not removing or not adding any heat to the system. So if it's adiabatic, always remember Q here is equals to 0. Right. If it's non-adiabatic, you have to consider the Q. Because where does this Q comes from? So I'm going to go back to our slide. Okay, this one. Kan coolant masuk, coolant keluar. So there is some Q there. And how do you calculate your Q? MCP delta T. M dot. If you don't remember, please remember. So you have this heat capacity. And of course, you have your delta T. Okay, and the delta T formula depends on the change of temperature depending on which heat equipment that you used. All right. So very good. So we are going to sekarang 11:06 sekejap lagi. This is very important, yeah. Also very important. In almost chemical reactor, kinetic, potential, and other energy are considered negligible. So your E here Your E here, nampak asli E, and that E is equivalent to your internal, your potential, your kinetic or others like electricity. So here in chemical reactor, we are assuming there is no kinetic energy, there is no potential energy, and that is all those are considered negligible. What is left is the internal energy only. All right, so that is one thing. Then enthalpy, heat transfer, and work teams are not negligible. Then we are only going to consider the enthalpy, the heat transfer, of course. If it's adiabatic, then you simply say Q equals to 0. And of course, you have to consider the work energy, the energy from the work. Work ni apa? So the question would be, how do I define the energy from work? What kind of work? Bekerja jadi engineer ke? Bekerja jadi cikgu ke? Bekerja jadi apa-apa ke? No, we are talking about the work in your reactor. Yeah, what kind of work? So here, we are going to consider what is left is the work from the flow coming in, from the flow coming out, because you have your reactor there. Of course, you have flow coming in and flow coming out. So the work is considered as one of the energy. And the energy changes through time. So we call it rate of energy. Entering the reactor, added by the mass flow into. Okay? Coming out, rate of energy. Added to the system, of course, but at the outer stream, flow coming out to get the mass out from the system. So that is also work. All right. And we write that formula based on the F, P, and V tilde. And that V tilde is a specific volume, yeah, specific volume unit. Yeah, we're gonna go to that slide later on. So this is what you see. Yeah, why I do this slowly, because it's very crucial that you understand your overall scenario. Apa yang you ada dalam sistem you. So that you can write that in terms of formula. You don't simply memorize formula. You have to write it from your heart. And unfortunately, at the beginning of topic 7, there are so many formulas. Yeah? And you have to understand that. So we start with that basic formula. And we simply now, tadi kita buat assumption, tinggal internal energy. And we have your flow here, flow F, which is the same F coming in. But energy here, not only the internal energy, also from the flow work yang coming in and flow work out. Of course, plus the U here, right? So that is why kat sini I ni, and that whole thing is what we call as enthalpy. All right. So the internal plus the flow work. Okay. So and simply substitute it to here, so you can rewrite that equation. The change of energy in your reactor is simply the Q minus the work plus the F times the enthalpy in minus the F times the enthalpy out. And your enthalpy including the internal energy and your flow work. Okay? And so this is quite a very good reference so that you can remember it. So let's say if you have your reactor here, so what coming in is simply your flow times the enthalpy, and of course you have your Q, then and flow, enthalpy, and the work done to the surrounding, yeah? All right, and coming from the system. Then please refer to the units as I wrote here. That's the same thing, We simply rewrite that equation. It's the same thing there. I'm going to go to the next one. It's simply the comparison between the isothermal and the non-isothermal, for example, in a PFR. As you know, for an isothermal, okay, isothermal, daripada topik 1 till 6, isothermal. Non-isothermal, your topic now. Okay, just recap. This is what you have learned so far. You say the temperature is constant. You say the pressure is constant. Since the temperature is constant, your K is directly considered as constant. Then, since this is PFR, as tau increases, cos PFR, masuk, tau, V increases, yeah, as you go in and go out. For a liquid phase, you assume if liquid phase volumetric flow rate is equivalent to the initial volumetric flow rate. Conversion depends on the K, of course, the temperature, and constant initial concentration of the limiting reactant and increasing tau. So that is isothermal. So those are the formulas that you have covered from topic 1 till 6. And that is the basic design formula for PFR. And that would be your concentration profile yang you belajar akhirnya to plot it either by your first prediction or you prove it by using polymath, for example, yeah. As time increases, reactant decreases, product increases, conversion increases. Right? Ini topic 1 till 6. Now, in topic 7, since you know the temperature changes, so as the volume, PFR, the volume increases, volume. Okay? The T increases. If it's exothermic, so increases. Since T increases, K also increases. X also increases. Okay, look at the plotting, yeah? So you have V equals to 0 here. Of course, the X also X naught, right? The K, it starts at a certain value. So of course, the K depends on the temperature, yeah? So the K also has some value. Dia tak start 0 lah. So the temperature, of course, depends at certain temperature that is entering initial. So dia tak start dekat 0. Okay. So this is how you make sure that you know how to draw your plot. Okay. So in this case, since we are dealing with non-isothermal, the temperature is not equivalent to the initial temperature. The K, of course, not constant because of the non-isothermal. And the K is, of course, is a function of temperature. Yeah, the K depends on the temperature. As temperature changes, your K is also changing. All right. So for that, we need an energy balance. We know earlier we can only make a relationship of the K to the change of temperature. Yeah, this is your temperature reference. This is your temperature. T1 is your temperature reference and this is your new temperature. So you want to find your new K. Yeah. So you have a relationship of K to temperature. And you know earlier, you have a relationship of your X to T. Yeah. You have the relationship of V to T. But now we want to have the relationship of X to T and T to V. Yeah. In your PFR, what would be your X to the change of the volume and also the temperature for a PFR in a non-isothermal condition? The only way to find that relationship is to form your energy balance. Yeah. So the energy balance is to solve for your X, which is depending on your T, and your T, which is depending on your V. So therefore, it is interconnected to each other. All right. So that's the purpose of writing your energy balance for non-isothermal condition. So we're going to take our first 5 minutes break. Before we take our first 5 minutes break, do you have any question? Adriana?
No question, Doctor.
Thank you. Ashikin.
Saya pun tak ada, Doktor.
Najwa.
No, Doktor.
Noren.
No, Doctor.
Khairia.
No, Doktor.
Mashita.
No, Doktor.
Azian.
No, Doktor.
Kamilia. Kamilia.
Kamilia pergi toilet.
Kamilia kita lihat. Okay. Macam mana Mashita tahu? Okay, so I'm going to give you 5 minutes break, yeah? All right? Hah? What? Saya dah buka music. Kenapa tak boleh? Mic sekarang tutup ke tak ni? Okay, Assalamualaikum warahmatullahi wabarakatuh. I'm back to the class now. Are you also back on your seats?
Yes.
All right, very good. I'm going to spend another 5 more minutes for the energy balance topic. Then we will go to our next activity, which is your presentation. Maybe maybe we're not going to spend all of the time for everyone to present. Tak tahu mungkin tak cukup masa ke apa. But if you don't have class lepas ni, so you can decide to finish up, or maybe you need rest for the next class in the afternoon. Ada kelas kedua ke? Yes, so you need you need rest definitely, yeah. So I'm gonna spend an additional 5 minutes to touch a little bit more on the energy balance, which I find it very interesting. Yeah. So we are on mana pen saya tadi? We are on this slide. Okay, I'm gonna go back. Yeah, slideshow. Dah nampak kan? You can already see my slide, right?
Yes.
Yes, Doctor.
Good. Now we are on this slide showing you the scenario of adiabatic and non-isothermal, right? It's a non-isothermal naturally condition for your reaction. So we are talking about an adiabatic system, yeah? So definitely your assumption starts with the non-isothermal having the temperature initial is not the same as the temperature, let's say PFR. This is temperature initial. Then there is temperature, yeah. We got T1, T2, T3, T4. Definitely all the temperatures are not the same to the temperature initial, right? Because of the exothermic, let's say. But the temperature initial is temperature naught, which you assume here, yeah? Temperature naught is the temperature at T equals to 0, for example, or you tag it as Ti, initial. And because of that, K is not constant. And the K is a function of T. The K changes because of the non-constant temperature. And if adiabatic, the heat capacities of the species are equal, so that is again another assumption that you can use. If it's adiabatic, so you can assume Ca equals to Cb. If you are dealing with the two components, then you can say that for an adiabatic system, if the heat capacity of all the components are close to each other, then you can say delta Cp is equivalent to 0. Yeah, the change of the heat capacity from different components. Yeah, and if adiabatic, heat of reaction is constant. So that is again another assumption that you can use. If adiabatic, the heat of reaction is constant. Yeah, take note that throughout this chapter, you will see how we write the symbol, yeah? Delta H, or H, then delta H, then we have delta H with this degree sign. So let's say yang ada degree ni, it always means because we are taking that enthalpy, and because of the delta, so it's a change of the enthalpy with reference to temperature reference. So TR here, reference, and that temperature reference is always chosen as at 25 degrees Celsius. All right. So if you see ada degree sign kat sini, it always the change of, let's say, enthalpy, the change of the enthalpy with reference to the enthalpy at the reference temperature, in this case chosen always at 25 degrees Celsius, right? So here, kat sini ada pula lagi satu subscript with a capital R. So here dah settle with reference to the temperature at 25 degrees Celsius. We have another subscript R there. It's always referring to the heat of the reaction. Yeah, delta H there, always the heat of the reaction. Yeah, in this case, it says for an adiabatic, the heat of the reaction is considered to be constant. Now, take note. This slide somewhat dia skip banyak benda but you will see that banyak benda before it reaches to this formula comes from tutorial 3. We will do that later on once you reach that tutorial, how we get to that temperature. Meaning, if you want to know the temperature for that adiabatic or non-isothermal system, in this case, it depends on the initial temperature yang masuk tadi. It depends on the X. It depends on the heat of reaction. Of course, we got this degree sign. It means the heat of reaction change with reference to the temperature, reference at 25 degrees Celsius. In this case, TR here, reference temperature, we choose 25 degrees Celsius, and CP is the heat capacity. Okay, so just take note first. How do we get to that formula? Later on, we'll see, right? 1 minute ke? Another 1 minute. All right, so for an adiabatic system, what would you do is, since we know the temperature is not the same as the temperature initial, and the K is not constant. So therefore, the X is depending on the T. If it's PFR, the X is also depending on the V, yeah? And the T is also depending on the V, all right? Untuk non-isothermal. Okay, so what we need to do is, of course, we want to know the conversion. So we don't know the conversion. So let's say if you have a target conversion, so choose your targeted conversion. Then you know, let's say PFR, dia masuk T0, dia keluar T. Okay, so what you want is your conversion at the outlet of your PFR, let's say. So once you have your target conversion, so of course you choose, you can calculate your T, right? So of course this changes. Tapi bila dia keluar at certain temperature, that temperature will cause certain achieve X, yeah. Tapi X you nak, you dah tahu dah X apa you nak. So you need to know your T, okay? First you choose your X, then only you can choose your T. Once you know your T, then only you can calculate your K. Then having all that, then you can calculate your rate of reaction. Then having your rate of reaction, okay, you can simply plot. You have FA0 there. Plot with the y-axis, FA0 over the rate of reaction against the conversion. Yeah. For an adiabatic system, weirdly, the typical curve would be like that. Yeah. So dia tak ada turun je, naik je, dia boleh turun, dia naik, atau naik, dia turun, macam tu. So that is adiabatic, yeah. So I'm going to stop here first, and we are going to proceed to our next activity. Atau you nak proceed dengan energy balance lagi? Atau rasa interesting nak sambung lagi? Macam mana? Fazlika. Oh, Fazlika.
For me, saya okey je mana-mana.
Okay je mana-mana. Nanti bapak tanya nak kahwin dengan si A ke si B. Saya okey je mana-mana. Macam mana? Amani gelak. Ada
lain,
dua
doktor.
orang datang nak meminang. Tu mak dengan ayah tanya. Mana satu? A ke B? Mana-mana je okey. Fazlika ni. Fazlika, jawab semula soalan. Nak I teruskan ke nak activity presentation?
Saya teruskan.
Okey, teruskan.
Tapi boleh tanya juga kat classmate yang lain.
Okey, kita tanya kelas rep S1. Where are you? Azwan,
Ya, doktor.
teruskan ke nak presentation?
Um, uh, saya ikut doktor. Kalau doktor rasa boleh teruskan, doktor teruskan.
Kata orang datang webinar, saya ikut awak lah, awak suka saya tak? Soalan jawapan. So saya teruskanlah. Susah sangat nak jawab. Okay, can we go to the next one, yeah? Because I think it's getting interesting, yeah? So this is the steady state energy balance equation. Now, when I'm going to go to our previous slide, huh? Okay, previous slide, saya scroll back. Allah laju pula. Okay. Saya cubalah delete this writing. Alah, tak boleh delete eh? Oh, sebab saya dah tutup tadi. Okay. So this equation 11.3. On your left hand side is the rate of accumulation of energy. Betul? On your right hand side is all the summation of the energy lah. Okay. The Q, the work, the flow in, the flow out. Betul? So why this 11.3 dia kata unsteady state? You tell me. Najwa. Why? Why this equation 11.3, the assumption made here is unsteady state. What do you mean by steady state? What do you mean by unsteady state? Najwa.
Masih tak ingat doktor.
Tak ingat? Nada. Ish. Kurang ni dah belajar semester 4 ada steady state dan unsteady state. Ish. Shadiana.
Tak ingat doktor.
Okey, tak ingat lah. Senang cerita buat cerita lah. Afsal lah, kita tanya Afsal. Kok Afsal dia ada jawapan advance final year tu kan dia dah boleh jawab dah. Afsal.
Ya, unsteady state sebab ada difference between dia punya flow in flow out. Kalau steady state flow in flow out sama.
Okay, if you are talking about the flow so we are very good. Afsal ni memang, ni betul ke kamu ni budak semester 4 kot kamu? Kelas 8 kot, pergi patah balik ke apa? Just kidding. But anyway, very good. So steady state means if you apa-apa dalam dunia, in any condition, it always starts with unsteady state. Ya, contohnya macam you duduk dalam bilik you, siapa yang sekarang buka aircon? Ada. Okay, siapa sekarang buka kipas? Okay, semua buka kipas angkat tangan. Semua buka kipas. Siapa tak buka kipas memang terror lah. Duduk tepi laut kot. Terengganu. Okay, betul. So kalau you tak buka kipas, you bangun tidur, you masuk bilik, temperature sekian-sekian, temperature subuh. Dan bila pukul 10 pagi, temperature dah naik. Kata you tak buka kipas, what happens to the temperature of your room?
Increases.
Increases lah kan? Tapi you kata nak masuk kelas Madam Mizoni, Dr. Mizoni, my optimum temperature so that I can absorb all the information into hours, zap gitu. Temperature bilik saya mesti 27 degrees Celsius. So what do you do? 27 sejuk oh. What do you do?
Turn on the conditioner.
So you control the condition of your room, right? So you are introducing work there. The heat being removed by the convection. Kipas you pusing, the air surrounding tu lah yang akan remove the heat so that temperature panas daripada luar tu, matahari dah naik, masuk through dinding, ada panaskan bilik you, dia boleh control your certain temperature. So kata perfect lah you punya control ni, which is of course not. Why? Because your body is also releasing some heat. Kalau hidup static je tak bergerak, mungkin je. Tapi impossible. So, that's why we use the word assumption. Right? We are assuming the temperature condition or the energy or the whatever is reaching no changes. And that changes adalah berdasarkan time. So that is why you have here on this 11.3, the change of energy through time. If there is still change, energy berubah-ubah through time, then it is still considered as unsteady state. Of course, it's very hard to reach that steady state, yeah. Unless you punya design reactor tu memang sangat dahsyat, you boleh make it constant, yeah. So here, it is said to be unsteady because there is change, the change of energy through time. Meaning, it is not considered, I'm not going to answer that. I'm going to go to, before I go to that. What if you say now it reaches steady state? So what would happen to this? What would happen to the energy? What is the number that you would use if it reaches its steady state? Akasha? Very
Zero.
good. Zero. Sebab energy at certain time is the same as the energy at the other time. So the change is always energy 2 minus energy 1. Now they are the same, then it's considered to be zero, no change. So if you want to use this equation 11.3 for a steady state, what would you do first? The left-hand side is to be equivalent to zero. Okay, always remember. The same thing in your heat transfer. So I'm going to go to the next slide. So this is what you see for a steady state condition. Nampak? This is the same equation. Of course, tadi equation tu kita dah simplify until we use the enthalpy. The enthalpy, the work, the Q, and this is the change of your E circumflex over the time circumflex. Now this becomes zero because you are assuming steady state. Okay, so what is left is to know all the terms. Ni apa, ni apa, ni apa, ni apa. All right. So we are going to look into that one by one. Okay, let's say we are using this reaction equation. The A reacts with B producing C plus D. So every 1 mole of A, how much of the mole of B? How much of the mole of C? How much of the mole of D? Okay, for a steady state energy balance, we're going to go to the next slide. So we have the reactant A and B, inlet, outlet, then product A and B, inlet, outlet. Yeah, inlet means, of course, you have your PFR. A, of course, you feed in. B, of course, you feed in. Since A and B must react in the reactor at certain temperature, then we can assume C tak ada, D tak ada. But of course, in your mole balance or energy balance, you still have to write empat komponen ini, ya. Masuk ke, keluar ke. Okay. For the outlet stream, of course, you may assume A and B going to be zero if your assumption says, or maybe in your reaction, until certain time, the A and B are all consumed. So dia tak ada. So tinggal C and D. If it's not, then at the outlet, of course, you may still have B and A remaining or unreacted. But the C and D are the produced component. Okay? But the C and D here, since it is not yet produced, you may assume zero. But unless if it comes from a different stream, rupa-rupanya, oh adalah C and D ni. Tapi you nak enhancekan lagi dia punya conversion. So the inlet tu pun tak akan jadi zero lah untuk C and D. It depends on the situation, on your stream coming into your reactor. Okay. Next. Now, what are the steps that we can follow for this non-isothermal reactor design dealing with these two components being reacted to each other? First, of course, imagine this is the equation that you will need to solve. For a steady state, that is considered to be zero. The change of the rate of the accumulation considered to be zero. So we first is to write your F. What is your F? Okay, let's say your PFR. You have your F coming in and coming out. So, and of course, we are dealing with the enthalpy. You have your enthalpy coming in and coming out. So first, to write your inlet and outlet FH. Okay. Second, this is done, that is done. X. Now we don't know your F. F in terms of X. So what is this F in terms of X? Or theta. All right. Theta comes from the stoichiometric table. F, remember, it depends on your gas or your liquid. Then from your stoichiometric balance equation, then you may know your theta. If you don't remember, you have to flip back your notes, then tengok balik apa tu theta. But I'm sure you remember lah, you are doing your assignment now. It's a very good exercise. Then substitute all equations in step 2 and 3, having all that. So put it back in step 1. Then re-express this equation as steady state energy balance. So we're going to go into that one by one. Yeah. The first step. Write the inlet and outlet FH. Okay. But first we need to know what is entering. Yeah. What the H entering and the H leaving for all species. We know that we have A, B, C, D. Okay. So we're going to write for all species the summation of that formula. Yeah. So HI naught FI naught. Now, I remember topic 6, yeah? Lesson 1. Remember we used the subscript I and J. Okay? I and J. And I remember kalau multiple reaction, this is one single reaction, multiple reaction, the I refers to the number of reaction. And the J refers to the species. Okay, itu multiple reaction topic 6. Now we are in topic 7. Somehow, okay, jangan got stressed out because of the subscript. It is defined in topic 7. The I is the species. Tapi topic 6 tadi, the I is the number of reaction. Ya, itu untuk multiple reaction. Okay. When you read your nota, tiba-tiba Allah sekejap, idea apa, pening, dah stress nak exam esok. Tak mau. Okay. So I tell you from the beginning, yeah. So always look at the definition of the symbols used. Tak kira lah subscript ke apa ke. Okay. So in this topic 7, the I used is for the species. A, B, C, D. And inert. Alright. And the inert comes from, let's say it's in the air, then the inert could be the nitrogen from the air, for example. Okay, so the naught is referring to entering, yeah, at t equals to 0. Leaving, simply the I lah. I of the A, B, C, D, inert. Okay, first thing. Second step, express the F. Now, want to know how to find how to get the value of the F. And the F depends on, so this is what you did in your previous topics, stoichiometrically how you write the molar flow rate for each of the species. Yeah, the molar flow rate according to the initial molar flow rate. Then of course you got the theta. Theta means the relationship of the molar flow rate initial over that particular species at initial time. Yeah. Then of course you have, of course this one is the mole, yeah, the stoichiometric ratio for that specific species. Okay. Next, Step 3. Once you have all that, so that is the basic equation that you extract from that part, from your energy balance. Simply substitute the step number 1 and step number 2 inside, yeah, inside that formula, yeah. So whatever that you see here is the not to say summarize, to see the factorize mathematically being expressed, yeah. So that insert masuk, that is the formula that you can write, yeah. Simply that dia tak tunjuk step by step lah, but you can try it on your own. You will get this final equation. And from the 1113, we see that this part, that part is actually this part. And that part is considered to be the heat of reaction at temperature T. The heat of reaction at temperature, at certain temperature. Remember when I say TR? TR means temperature reference, which is 25. Here at that specific temperature. So kalau temperature changes, so what is the heat of reaction at temperature 100? What is the heat of reaction at temperature 200? What is the heat of reaction at temperature 300, for example? Yeah. How to get that? Simply by knowing the HC, HD, HB, HA at that same temperature. All right. So how do we do that? How do you do that? It's next slide, but I'm going to go to the next step, which is once you have all this, okay, substitute it back to the energy balance equation. Then finally, whoa, Jaya. Okay, finally the simplification is done by writing the summation, all right? The summation, okay, of the species, all the species, hold on, yes, all the species to whatever species that you have, inlet minus outlet. Then this is simply yang banyak-banyak ni, this one. Kita simplifikan ke sini, alright? Okay, that will be the simplified equation. So use this form of steady state energy balance if enthalpies are available. Of course, meaning if you know your enthalpies. Okay, now, so that will be your simplified equation, and we are going to start using that simplified equation. Now dia kata, of course, you have to know this H. So how to know this H, right? Let us start with the H outlet, meaning if you have this PFR, H inlet initial, that is H. So remember the I is species, yeah, species. So dia tak ada initial, so this is final lah, which is H, that species coming out from that reactor. So how to find this one? Dia kata how to find this one. So to find the enthalpy that is coming out from that reactor, depending on this equation. And what is that equation? So HI, remember that degree sign? So it means enthalpy formation of species I at reference temperature TR. Reference temperature TR at reference temperature TR, usually at 25 degrees Celsius. Okay. HI is of course the molar enthalpy of the species, so the enthalpy coming out from that reactor. Delta HQ, I is that species. Delta means change of enthalpy due to change of temperature from TR to T. Okay, so that is delta HQ. Change of enthalpy due to change of temperature from TR to that T, that temperature. Okay, this is how you find your enthalpy coming out from your reactor. Now, this is done. Okay, this is done. HI coming out from your reactor. Now, the big question is, what is this? Change of enthalpy due to the change of temperature to TR. Alright, meaning change of enthalpy from one T to another T. Yeah, so simply the change of the heat capacity through time. Yeah, from T1 to T2. So that would be the change of enthalpy. Okay, if you don't know your CP, how are you going to know your CP? Of course, like my usual answer would be, kita tanya saintis lah, apa CP untuk komponen ni? At this temperature, apa CP dia? Now your job, you refer to the published data because you are engineer. Engineer tugas nak design, right? Unless your boss suruh you buat semua, okay? Buatlah eksperimen. Alright, now how to find this CP? Okay, either people publish that data and give you, or if not, then you can still solve it by calculating it using this common formula for CP. So you have this coefficient, and that coefficient must be given by the scientist to you. Yeah, from let's say using that correlation will give you a certain value of your CP. Yeah, meaning kalau T dia 100 degrees Celsius, then of course this is 100, that is 100 squared. Then you must check the formula is in Kelvin or in Celsius. If you don't check, then nanti you salah input, then you get a different value. Who will be your alpha, beta, gamma? Who will be giving you the value? Scientist lah. You can cari. Yeah, the coefficients. So okay, take note that we have the units for the CP in terms of BTU or calorie, and then of course all the units for the temperature is Kelvin for joule and calorie reference, but BTU we are using a degree R. All right. Now, take note benda-benda semua you buat masa you final year. Okay. When you do your design, if you don't know your CP, then you have to calculate your own CP at different temperature. How to get your alpha, beta, gamma? Please find it from the published data from Paris Handbook. Paris Handbook of Chemical Engineering. Paris Handbook of Chemical Engineers. Please take note. We, the chemical engineers, have this, kalau orang putih lah, we are Muslim, we don't say that. We have this big reference, dia panggil Bible lah. We don't say that, we are Muslim. So it's big reference, the whole world use it. Yeah, it's a handbook for chemical engineers. So you can get the alpha, gamma, beta from there, from the appendix, or from the whole handbook. Yeah. Now, ada lagi 2 minit. Okay. Because of that, so this is the equation to determine the enthalpy coming out from your reactor. Done. Okay. Now, this is done by using that formula. Okay. This is not yet done. Okay. Not yet done. Sorry. Yes. That. Done. That is the enthalpy of formation of the species, that particular species at reference temperature TR, which is 25 degrees Celsius. So that can also be determined, yeah, from scientists, yeah. So they will make reference to the reference temperature 25 degrees Celsius. Someone has to give it to you. If not, then we have to calculate it, all right? Next, now, tadi kita dah determine sini. Now, from that energy balance, steady state, we want to know this whole thing. Alright? And that whole thing is actually saying HI, initial, then HI. Okay, energy balance equation kata enthalpy inlet tolak enthalpy outlet. So, sebenarnya dia kata the energy added, yeah, coming into the system. Outlet going out. But when we have this gradient formula, normally we always refer to what is coming out. So kat sini H1, ni H2. If you want to find the delta H, of course, normally normal matematik biasa, H2 tolak H1, betul? So this is what you see, yeah? Okay, in reality mathematically, H2 minus H1. And that H2 is actually coming out, H1 is coming in. So simply, that is the set of formula yang kita belajar tadi. Reference to 25 degrees Celsius and the change of the enthalpy. Initial, yeah? No, coming, H2. Okay? This is H1. H1 tak ada titik. H1. Alright? Simplify that and you'll get this formula. Alright? Which is CP at that species times T minus T of that species initial. Yeah? So H2 minus H1 is positive. So if we are going to put that here, but in this formula is H1 minus H2. Alright? Because of that, now asalnya positive, now it becomes negative. Right? Sini sebab H1 minus H2. Yeah? But we have that information here, which is H2 minus H1. Yeah? So if it's H1 minus H2, then it becomes negative CP, T minus T. Alright? Introduce it to there, negative, so that is why positive ni jadi negative. Okay? So I'm going to stop that here. We're going to continue this later on. Okay, so thank you for your attention and we'll meet again next week. Yeah? Yeah, do you have any question, Hanani? Fazlika?
No, Doctor.
Akasha?
No.
Afifah mana Afifah? Oh, sekejap ada, sekejap tak ada. Amani? Afifah okey? Oh, tengok macam tu je mengeliat je. Azian?
Okay.
Hafsar?
Okay.
Okay, Nada, Nur Nada.
Okay, Doktor.
Azri. It's okay to say not okay, okay? Azri.
Okay, Doctor.
Yeah, it's too much today, but I hope with that too much adalah something you belajar. Ashikin.
Okay, Doctor.
Amelia. Amelia. Okay. Khairia.
Okay, Doktor.
Okay, Azra.
Okay, Doktor.
Najwa.
InsyaAllah okay, Doktor.
Syafiq. Apa-apa? Najwa kata apa?
InsyaAllah okay.
InsyaAllah okay, Alhamdulillah. Syafiq Abu.
Okay, Doktor.
Syadiana. Nampak muka lah Syadiana. Syadiana.
Okay, Doktor.
Adriana.
Okay, Doktor.
Mashita.
Biasa, Doktor.
Fazlin. Mana Fazlin? Amani. Dah ada. Kamilia. Mashita. It's okay to say not okay. Mirza. Adriana. Adriana dah. Mirza. Afsar. Daniel. Mana Daniel ni? Azwan. Mana Azwan?
Okey. Okey, doktor.
Daniel.
Okey,
Tadi
okey,
tak
doktor.
nampak Daniel. Ha. Daniel
Ada.
okey?
Okey.
Okey. Tunggu sebut. Sekejap. Khairina.
Okey, doktor.
Ya. Khairina okey? Okey. Raja kesiannya. Internet okey tak Raja? Raja and Syafiq. Umaira. Where are you, Umaira? Are you there?
Okay, doktor.
Umaira. Okay, very good. Raja punya Raja. Okay. The internet start. Okay, I wish you all the best. Thank you so much for doing your video, which we thought that we can play that in class, tapi we'll find some time to do that, nah? Okay? Alright. Okay, see you again. Assalamualaikum warahmatullahi wabarakatuh. Bye-bye.
Salam. Thank you, doktor.
Thank you, doktor.
Thank you, doktor.
Thank you, doktor.
Thank you. Okay, silakan abang tolong